Okay, good afternoon, everyone. So, as we know, the artificial intelligence has become one of the hottest topics in Taiwan in recent years, and the government has put a lot of money in this hot field. And in particular, the subfield of machine learning or deep learning has gained a tremendous progress in recent years as well. So people are wondering what applications or what are the potentials of these new techniques. And in physics as well, we try to understand better, or we try to make use of this new technology to help us learn physics. So today we are very happy to have Professor David Shi from Rutgers University to give us a lecture. And let me briefly introduce him. So Professor Shi went to college at Harvard, and in year 2000 he graduated and moved on to Princeton for a PhD in physics. And after 2006 he started his postdoc career, first at Harvard again, and then at the Institute of Advanced Study until year 2010 he joined Rutgers University until now. He worked on various topics in particle physics, first starting from supersymmetry and then more flavor physics, and now recently more collider physics. In particular, he in recent years he devoted to the research of using deep learning to study collider physics. As you can see from the title, today he will tell us deep learning and the LHC, a new era of collider physics. Let's welcome him.
Okay, well, thank you very much for the introduction and for the invitation to come give a talk in here. It's an honor and a pleasure and a privilege. Thank you also to the PPP 13 workshop for hosting me while I'm here. And apologies to my colleagues who may end up hearing a similar talk twice because the workshop's still ongoing. Okay, so I'm here to tell you a bit about the thing I've been interested in, I would say, most of all in the last couple of years, and it's sort of taking over my life. And that's deep learning and its applications to the LHC. So let me begin by just starting from what we already know. This is, in case you're not familiar, this is the standard model of particle physics. It's beautiful enough to fit on a t-shirt, and literally, so if you understand quantum field theory and have this Lagrangian that fits on a t-shirt, you could in principle derive every known fact about the standard model, and by extension, not to be too grandiose, but every in principle known fact about the universe starting from this t-shirt. So that's why a lot of us study particle physics and fundamental physics. And so just very briefly, there's three forces in the standard model: the electroweak, and the strong force. And the standard model has just 17 particles that you see shown here, and it has, if you count how many free parameters are here, it has 19 free parameters, which is a lot. That gives us hope that there's something beyond the standard model. So it has three forces, 17 particles, and 19 parameters, and it gives a successful description of nature. Of course, that's priceless, right? Okay, nobody got this joke. Okay. One person got the joke. Okay.
I'm American.
All right, so good. I'm off to a good start. So again, this is another view of the history of the standard model, according to the respected source, The Economist magazine. But this is, according to them, I think it's fairly accurate. I don't know if there are a few errors here, but anyway, it gives you the idea that of the history of the discovery of all the particles in the Standard Model, ranging from the electron in the 19th century all the way to the Higgs, just in 2012. And one thing you get from this is that the 60s were a golden era for discovery of the Standard Model. And another thing that you get, I guess, you don't get from this, but from my handy overlay, is that particle colliders have basically been the primary tool, I would say, most people would say, I think, for the discovery of the Standard Model since the 60s, since there were particle colliders. And shown in yellow here are hadron colliders. These are colliders that collide protons on protons or protons on antiprotons. And shown in blue are the E plus E minus colliders. Those collide electrons on positrons. And you can see that both hadron colliders and E plus E minus colliders have contributed to the discovery of the Standard Model. The most recent discovery, which you may have heard about, was done at the LHC, and that was the Higgs boson. So that happened, that was announced on July 4th, 2012, a day which will forever be called Higgs Dependence Day. So both the ATLAS and CMS collaborations at the LHC announced that they'd seen the Higgs boson with a fairly standard model-like properties, basically sitting exactly where it was predicted to be. And they saw it primarily in these two very clean decay modes, Higgs to gamma gamma, Higgs to 2 photons, and here Higgs to Z and an off-shell Z, which each decay to leptons, so Higgs to 4 leptons. And yeah, I said that, right? Yeah, I said the very respected source, The Economist magazine. Yeah. So yeah, that's we all read The Economist and learn physics from it, right? Okay, so we don't learn any economics from it, that's for sure. Okay, so anyway, so the Higgs was discovered in 2012, a very exciting day, and you can see here very clearly this red thing here. That's the Higgs boson sticking out, a peak above the backgrounds. Here, very clearly in the diphoton mass peak as well, all consistent at the same mass of 125 GeV. Okay, so that was sort of the last remaining particle to be found in the Standard Model, and it's sort of the capstone of the whole theory. So another thing to know about particle colliders is, of course, that they've been getting more and more powerful with time. This plot here is called the Livingston plot. It shows that, roughly speaking, the center of mass energy of these colliders has been growing exponentially with time. And you can see signs of a leveling off here, which is perhaps not surprising, because also the cost tends to balloon. So we don't have infinite money, nor do we have infinite energy, so eventually it has to turn upward. But anyway, it's been growing with energy, the energy has been growing with time pretty significantly, and this is where we are now today at the LHC. And the hope is that by smashing together elementary particles with higher and higher energies, we can probe deeper and deeper layers of fundamental matter and interactions. So that's the whole endeavor here. So as I said, right now, the LHC is currently the largest and most powerful, highest energy particle accelerator in the world. It sits here, just to give you a sense of its scale, it's sort of a geographically sized thing, sitting on the border of Switzerland and France, close to the city of Geneva. And so here are some quick stats about the LHC, to give you some sense. It's 27 kilometers long in circumference, the tunnel, and the tunnel sits 100 meters underground. The center of mass energy is 13 tera electron volts, which is a lot. And it costs about $10 billion. And employs, which is not a lot, if you think about it, especially because it gives jobs to 5,000 scientists from over 200 countries. So it's a big experiment in pretty much all regards. The actual LHC is a ring where the protons are accelerated and collide, and they collide at 4 different interaction points situated around the ring, which correspond, each interaction point, there sits a giant hulking detector, and each detector is itself an experimental collaboration consisting of thousands of people, thousands of physicists. So we have CMS and ATLAS are the general purpose ones, and LHCb is focused on the physics of the B quark, and ALICE focuses on heavy ion collisions. Okay, so just to give you a sense of the scale of the thing, this is a picture of the ATLAS detector sort of face on. You can see that it has this cylindrical or toroidal symmetry, and you can see by counting the stairs here that there are 7 stories here. So the ATLAS detector is 7 stories tall, and this is a person here. Give you another sense of how big it is. So this thing was lowered to 100 meters underground sometime in the late 2000s, and it's been there ever since. This is another picture of the ATLAS detector, just to show you the different components. So here the beams collide, that's the interaction point, and particles then radiate outwards from them, traveling pretty much at the speed of light. And it's picked up in all these different components here. Different particles are registered in these different components. This is another view of the detector, cross-sectional view, showing you how different particles like muons and electrons, different kinds of hadrons, photons, pretty much every kind of particle you can make in the standard model has a unique telltale signature as it passes through this detector. For instance, the muon is the only part, by design, the muon is the only particle, besides the neutrino, of course, that can make it all the way out of the detector and be registered here in the muon chambers. So yeah, so that's how we identify and reconstruct different kinds of particles at the LHC. So this is just you can't give a colloquium without having a video, I think. So this is a video showing you how the particles collide at the ATLAS detector. They're actually generated, well, I'm sorry, the video already stopped. They're actually generated in a smaller ring called the SPS, which used to be the main experiment at CERN. So this is how these experiments are built, resting on the previous experiment. And so this is a video of how they collide, and all the lines, colorful lines that come out of here are individual particles, hadrons and leptons and things that register in the tracker and then in the calorimeters. Okay, so what do we hope to do with the LHC? Well, I would say the physics program at the LHC has 4 main parts. So the first thing is to measure the properties of the standard model with increasing precision. So that of course is the foundation upon which everything else rests. Now we've discovered the Higgs, and it looks like it's standard model-like, but we tend to separate out everything about Higgs physics is somewhat separate from the standard model right now. So basically measure the heck out of this new particle, the Higgs, that only right now the LHC can do. So that's of course, that's a major effort at the LHC. Then there's the component of the standard model called flavor physics, which is the physics of all the different 3 generations of quarks and leptons and all their very intricate interactions with each other. So that's a major effort, especially, but not limited to LHCb. And finally, there are direct searches for physics beyond the standard model. Direct searches for new physics, as we call it. And so all of these different areas sort of interact with each other. They're not totally distinct, of course. And I would say, in the view of many, the goal of all of this, the overarching goal of all of this is to answer the question, what physics, if any, lies beyond the standard model. So even when we're measuring the properties of the standard model very precisely, our goal is to break the standard model. We hope that by doing such a precise measurement, we can find a discrepancy between the data and the prediction, right? So that's sort of what we're always trying to do here, is to break the theory and find out if there's anything beyond the standard model. And why do we think this is not a totally pointless task? Well, it's because we know that there's physics beyond the standard model, so we're sure of that. So for instance, we know that there's dark matter out there from lots of different observations. Complementary, overlapping, over-constrained observations tell us that there's that a significant part of the universe, in fact, is composed of dark matter, some invisible, gravitationally, probably only or mostly gravitationally interacting particle that sort of pervades everything around us, but yet we don't know what it is. We also know that the neutrinos have mass. That was a Nobel Prize discovery by the Super K experiment. and from many years ago. And so the source of neutrino masses also has to come. The source of neutrino masses is not on that T-shirt I showed you at the beginning of the talk. That has to come from something beyond the Standard Model. And besides these two, these are basically set in stone as sources of physics beyond the Standard Model. We also have other hints that there should be something beyond the Standard Model. For instance, why is the electroweak scale why is gravity such a weak force compared to the electroweak force? That's one way to say it. That's called the hierarchy problem. Or why are there these three generations of quarks and leptons with these really weird couplings between them? So there's all these different hints, and in some cases more than hints, for physics beyond the Standard Model. So far though, the LHC has been running for about 9 years, and we haven't seen any sign of new physics at the Standard Model. This is a plot, for instance, showing you all the different cross sections for all the different processes, things that could be produced in the Standard Model. And you can see for one thing that it spans 14 orders of magnitude here. And each one of these things, each one of these points here is both a prediction and a measurement. And so at least in this logarithmic scale, which of course hides a lot of details, you can claim that there's very impressive agreement between Standard Model predictions and the measurements. So far the Standard Model measurements have not broken the Standard Model. And just to give you a sense of when we do a direct search for new physics, this is where we're at. We're about maybe 11, could be like 11 or 10 orders of magnitude, smaller cross sections compared to the biggest cross sections at the LHC, which is PP going to anything. So that's the sort of new physics that we're searching for, how rare it is at the LHC. Okay. And so so we've also done direct searches for the LHC, for new physics at the LHC. So here is a unreadable plot. So each of if you zoomed in very closely, you could see that each line here is a separate search for new physics that's done, in this case, by the ATLAS collaboration. And these are all searches for something called supersymmetry. And each colored bar here is a limit that they set on the mass of some new particle because they didn't see it. And so there's basically been many, many searches, hundreds of searches for new physics beyond the Standard Model, and so far nothing but limits. So no evidence of any sign of new physics. Just whenever they don't see something, they can set a limit on the new physics, on how strongly interact or how heavy or how light it could have been. Okay, so this is this is a plot now to give you a sense of where we're headed. This is a plot of the future and also the past for the LHC. So we are here right now in 2019. We're in the middle of what's called a long shutdown. So the LHC shuts down for several years at a time to allow repairs and upgrades to be made to the detectors. And so we're in the middle of one here. And then the LHC is going to turn back on again in 2021 and run for 3 more years. In its current state, and then there's going to be another long shutdown, and then you see that this is basically what's called the instantaneous luminosity of the experiment, which is a measure of how intense the beams are. So you see that right now we're here at 2 times 10 to the 34 inverse centimeters squared inverse seconds, and something dramatic is going to happen roughly in 2026, which is that it's going to jump by about a factor of, I guess that's only a factor of 3 or 2.5. But anyway, the experiment's going to become much more intense, and as a result, the amount of data it's going to collect is going to grow more rapidly. So this is the integrated amount of data that it's collecting as a function of time. And so you see that where we're here now, we have this much data. So this is 140 inverse femtobarns. Or so, and we're headed to up here to 3,500 inverse femtobarns if all goes according to plan. So that's basically what I said there, and so the amount of data we're going to collect is about 20 times more than we have right now. So we're sitting on just 5% of the total data set, and to get there, it's going to be another 20 years or so. So it's a long-term thing. And I think basically this whole thing is funded to some extent, so it's going to happen. So that's going to be a big part of the future of particle physics for the next 20 years. And so the question, especially during this long shutdown, where we all have some free time, so the question on everyone's mind is, look, going forward, we know what's going to happen. So in terms of the experiment, so how do we maximize the discovery potential of what's going to be this enormous data set? How do we make sure we don't leave any stone unturned in this data set? Right? It would be a shame because it'd be a shame if we missed the new physics because we weren't looking for it in the right place. Okay, so this is just a plot now showing you what's going to happen in the future to these limits that I showed you here. You can take any one of these limits, say, I don't know, a limit for, I can't even read it. Anyway, a limit for Luino production or something. You can take any one of these limits and project it into the future, assuming making some very naive assumptions. So that was what was, and actually get a pretty accurate answer. You can basically assume that things are going to scale with the parton luminosities for the experts. And so the assumptions are explained here in this website basically by these two, Gavin Salam and Andy Violet. Okay, so if you take the existing current limits, and project them to the future, you'll find that they're going to follow a curve that looks like this. So if we're starting here now around a TeV with a limit, the limit is going to scale, it's going to grow like that, assuming the status quo. So that's assuming that we don't change anything dramatic in the way we do the analyses. And so that's where we started in 2015. This is where we are now. In 2023, that's the end of the regular LHC run. We'll be here, and after another 14 years, we'll be here. So what I would take away from this plot is, first of all, that you can check that this curve is very close to logarithmic, and proper to logarithm is that it shifts by a constant amount when you double the argument. So a multiplicative factor of the argument is a constant shift of the logarithm. So what that means is that you only get a linear gain in sensitivity for a doubling of the data, for multiplicative factor. And eventually the doubling time of the data is going to become infinite. So after you pass this point, the data is not going to double anymore. So what I'm trying to say is basically that the characteristic of this logarithmic growth is you have what looks like early rapid progress in the growth of the sensitivity or the limits or the discovery potential, but then that plateaus in the future. This is characteristic of colliders. It's not a surprise. You only get a big gain in sensitivity when you increase the energy or when your data set is growing exponentially. Okay, so I like to think of it as the following. We're passing, so basically this rapid phase is going to end soon, and we're going to enter the slow phase. And the rapid phase I like to think of as analogous to the early days of oil exploration, where you could basically dig a hole in the middle of nowhere in Texas and get all this oil spurting out like that, and then make $1 million or something. So those were the early days of the LHC, where you could basically grab all the low-hanging fruits, look for new physics, not work too hard, and hope to see something spectacular. Okay, so those days are coming to an end. Now we're entering something like peak oil, or the era of scarcity. And so in the future, if we stay with the status quo, that is just digging holes in the ground and hoping for oil, the data taking rate is going to plateau. No increases in energy are foreseen, so we see that there's much slower progress. To maintain the rapid growth and sensitivity, we're going to need more new sophisticated analysis techniques. We're going to need some innovation here. We're going to need some new ideas. And also, in this enormous data set, we're going to need to make sure that we haven't overlooked any subtle and unexpected signals of new physics. So that's a qualitatively different thing that I'm saying, is that even I think I tapped this. Okay. Okay. Now it came back. Okay. Sorry about that. I'll stand a little closer here. Yeah, so a totally separate point is even if we're not interested in growing these discovery potential faster and faster, even if we just take this data set as it is, we need to make sure that we didn't miss anything, right? So that's a totally different point. And but either way, I think what we need are new, more sophisticated analysis techniques, and we need new ideas for how to look for the new physics in the data. And so what we need is something like fracking, which is how we get the oil that's buried beneath all the easy oil, right? And we need to never mind, what it does to the environment. So that's what we need. We need even more clever ideas than digging a hole in the ground. And so, in the subject of my talk is deep learning, and I think a lot of people are very excited in particle physics are very excited about the potential for deep learning to to supply these new ideas and new approaches for how to find the new physics in the data. Okay. So now I'm going to move on to the part of the talk where I talk about deep learning. So as you all, I'm sure, know from reading the news, the artificial intelligence revolution is here. The machines are taking over, right? And we have all these amazing things like image recognition, self-driving cars, Go playing robots. The phone knows what you're going to say before you say it, that sort of thing. You can do weird things to celebrities' faces, very creepy stuff. And of course, translation is, I guess it's far from perfect, but there's hope that it'll get there. And so all of this stuff is happening just in the last, 5 years, I would say, or yeah, less than 10 years. So deep learning has produced so many stunning successes in recent years in the real world, and is starting to have an impact in physics. Machine learning algorithms are now capable of performing human-like tasks, such as things that were not thought to be possible by computers before, like recognizing and classifying images, saying that this is a dog, that's a chair, that's a cat, and also understanding and producing natural language. So where are these successes coming from? Why is this all happening now? It's a convergence of three different things, three different factors. So one is that computers, of course, are growing more and more powerful every year, and they've reached a point, especially with these things called GPUs, where they're powerful enough to handle the kind of machine learning algorithms that are capable of doing these things. So it just reached a threshold. So hand in hand with that, people have been engineering and tinkering, and improving, innovating different kinds of machine learning algorithms that are well adapted to different kinds of tasks. And so given the increased computing power, we're able to play around with these algorithms and improve them significantly, find out what works. But the biggest thing that's happened, I think, is that, even setting aside all this, the amount of data that is out there and that computers can store and handle has increased dramatically. So just think maybe there's young people in the audience who can't even remember a time before Google or Google Images or Google Books or whatever it's called, where things were not digitized. You actually had to go to a place called the library, so now all the books have been put basically online somehow, right? And so you can access all these pictures, millions and millions of pictures. So you may imagine, you may not know there's a time when you took a picture and you had to develop something called film. Yeah. Okay. So yeah, everything's digitized now, and so that's all fodder training data for these machine learning algorithms. Okay, so that's really what people are saying, is that this is the prerequisite for deep learning. So even if you have powerful computers and stuff, if you don't have the data, you can't learn. You won't succeed. So you need large, complex, and hopefully well understood data sets. Okay. So, and what we are appreciating in the field of particle physics is that the LHC and colliders in general are the perfect setting for deep learning. I mean, considering all the different sciences, we're in actually one of the best situations to play around with these and be successful with these deep learning methods. That's because the data is humongous. We have billions of events on tape. Each event is very complex, hundreds of particles per event. And so this all adds up to petabytes and petabytes of data. And we understand this data, relatively well because we understand the standard model. So actually, we understand this data amazingly well, right? Because we understand the standard model. And also important for machine learning is the ability to generate labeled data. That's data where you know every single thing that happened in the data. And of course, in true data, we don't have perfect knowledge of it, but in simulations, we do, right? So we're also in a good situation here in particle physics because we have extremely accurate simulations based on our understanding of the standard model and based on tuning these simulations to many, many experiments that have come before us. We have these amazing simulations that can generate really realistic looking fake data, which can then be used to train neural networks. Okay, so before I get into the LHC applications, I just want to maybe spend a few slides on, because maybe this is new to you, about what is actually deep learning. So I get asked sometimes, what's the difference between deep learning and machine learning and artificial intelligence? So these are all buzzwords, and there are slight differences in what they mean. So I think this is basically how you should think of it, is that artificial intelligence is an overarching goal and refers to any computer or machine that can learn or reason like we do, or better. And a particularly recent successful implementation of AI is machine learning and as a subset of that, deep learning. So machine learning is basically any algorithm which can learn from experience, learn from examples. And in practice, what this really means is you feed the algorithm a data set, and it fits a function, a very, very complicated function, potentially with millions of parameters, but it fits this function to the data. And in doing so, it enables you to make predictions given new data. Right? Now you have a function, you can feed it new data and get an output. So that's basically, so you may hear people say that machine learning is just glorified curve fitting. And it is, it's like curve fitting, like your least squares, chi-squared method curve fitting taken to a super extreme. And the amazing thing is that empirically it works. And also the tantalizing thing is that nobody completely understands nobody understands really at all why it works. But it seems to work. And a subset of so machine learning can encompass lots of methods, like you may have heard of boosted decision trees if you're a particle physicist or work with data in any way, principal component analysis, all these support vector machines. There's lots of machine learning algorithms, but a subset of them which have proven to be particularly successful in the last 5 years are things called deep learning algorithms. And this is a class of machine learning algorithms whose fitting functions consist of multi-layer neural networks. So that's a particular class of functions you can think of. Okay, this is a little bit more about the history of the subject. So going all the way back to the 40s and 50s are when some of the seminal works on AI were done. And that sort of petered out. And then machine learning kind of took off again in the 80s, 70s and 80s. This is when various things like support vector machines, the first convolutional neural network, boosted decision trees were developed and deployed. And during this time, actually, collider physics, particle physics was a leader in applying machine learning techniques to data. So then things kind of, especially with neural networks, kind of petered out again until basically this decade, when there were huge breakthroughs in deep learning, and so now everybody wants to go work for Amazon or something. Okay, so that's sort of where we are. And so now the main tool for doing machine learning are neural networks. They've really taken over. And this is the basic building block of a neural network, in case you've never seen it. It's very much biologically inspired. Everything I know about neurons is on the slide, though, so don't ask me anything about that. But anyway, you basically have an input which connects to a neuron. This is the neuron. And the neuron can receive multiple inputs in principle. And the input here are called X. And how important these inputs are governed by these things called weights, W. So maybe the neuron only cares about pain from your finger. And so this weight is high and this weight is low or something. So that's sort of the idea. And you sum together all these weighted inputs and you feed them to something called an activation function, which basically tells you how big this input has to be before it sends out an output. Okay, so that's a model of how the neurons in our brain are supposed to work. And the hope was that if you wanted to design, the hope since the 40s, I think, has been if you wanted to design a human-like intelligence, you should try to mimic what the brain is doing. So that's by no means rigorous, but that's the sort of inspiration that people have been taking off and on, since the 40s. Okay, so this is an example of a neural network, a particular kind called a fully connected or dense neural network. This is the input layer. It consists of a bunch of, each of these circles here is basically a real numbered input, real valued input, and that gets fed to what are called hidden layers. So think of this as your sensory organs or whatever, and this as the hidden processing in the brain. And basically all these neurons light up with their activations, and finally they feed out to an output. It's like, do I jerk my hand away from the fire or not? And so in practice, this output is another number. Often it's a number between 0 and 1 if you're, for instance, trying to train a classifier. And so what this is really, after you write it all out, is just a very, very complicated looking, sort of recursively defined function. This is all it is. So the input goes here, and I feed it to this function. And so the magic of deep learning is that functions of this class, for whatever reason, appear to perform very well at fitting complex data sets and then generalizing to new data. Okay, so just a bit more about what you can use, what people often use neural networks for. The most important thing in the whole world is to tell whether a picture is a cat or a dog. So we spend an inordinate amount of time training neural networks to do that. If you think about it, though, it's very non-trivial for a computer to do this, right? So what do we do? What is the breakthrough that works? Is we feed it pictures of cats and dogs. We don't tell it anything other than these are all dogs and these are all cats. We don't tell it, features like the cat has, cute little ears and whatnot. We don't tell it any of that stuff. We just tell it that these are cats and these are dogs, and then it has to fit this very complicated function to the truth labels. And so basically it should produce an output that is the probability, the likelihood it thinks, or the confidence it thinks that the picture is a dog. Okay, so the goal of training a neural network is to minimize this loss function here, which takes the truth labels and the neural net output. And basically this loss function should be 0, should be convex, and should be 0 only when you have the right answer, and otherwise grow. Okay, so two common, just to give you some examples, people often use the mean squared error or the binary cross entropy as two common loss functions for training these things. You can see that they're both 0 if and only if, they're both positive definite and 0 if and only if the labels are equal to the neural net outputs. Okay, so the thing that makes neural networks so powerful, the thing that makes them special among all the machine learning algorithms, is that they alone seem to be able to learn from raw, low-level inputs, like the raw data. So this is the raw data in this case, the pixels in the image. So that's what deep neural networks seem to be capable of. And in doing so, they automate and also optimize what's often in this field called feature engineering. So, and this is why deep learning is able to massively outperform other machine learning methods. So you can think of this image recognition task as traditionally as you would a human would figure out all the things that make, say, in this case, a car, like it has 4 doors and wheels and shiny, and then maybe figure out a way to quantify all these features, and then you could feed those to a machine learning algorithm or a simple cut-based method and produce a classifier for cars or not cars. Deep learning is capable of extracting those features directly from the data. Currently, we don't have a good way for it to tell us what it learned, but it then feeds whatever features it extracted to its own classifier. So it makes it the black box bigger, but that's why it's more powerful. Okay, so just briefly about CNNs, convolutional neural networks are a special class of neural networks that really led the breakthrough in 2012. This all came basically from trying to get computers to do better image recognition. They were first invented in 1998 by these people, and the structure is basically built on the 2-dimensional structure of a pixelated image. And the way they work is you drag what's called a convolutional filter over the image, and that produces hidden layers, which are also images, until finally you get to the classifier output. So the first CNN that was invented had 5 hidden layers and was able to achieve 99% accuracy on a standard task, which was recognizing handwritten digits from 0 to 9. Okay, so that was considered pretty good, better than all the things that came before. But people quickly got discouraged because when they tried more sophisticated machine learning tasks, image recognition tasks, such as this one, a database called ImageNet, which has over 1 million images that are in color and of all sorts of different things. This is vastly more difficult than handwritten digit recognition. People found that this LINET thing did not generalize well to these more complex tasks. Okay. Gotta make that go away. All right. So then other ideas such as support vector machines took over, and finally things changed in 2012 when these people showed that a much deeper CNN, the way to make the CNN win is to go deeper. And that required them to innovate in how these things are trained and some tweaks in the activation functions and things, but the result was quite dramatic. They were able to do better than all the other machine learning algorithms in the ImageNet challenge by a factor of 2, I think. And so basically the thing that makes this powerful in the end is going deeper. And so this thing has, I think, 8 layers instead of 5, with many more parameters involved. So 60 million parameters. And this required them to train the thing on a GPU. So that was the first time a GPU was brought to bear on the problem. And that's when things really took off in 2012. Okay, so now this brings me back to the LHC. So what are we doing with deep learning at the LHC? It's a very active area. There's lots of different ideas being explored right now. By far the most well-explored and sort of successful area right now that's going to be closest to implementation in the experiments is in something called supervised learning. That's where you train on labeled data, like the image classification tasks. And so classification, you can map classification to various tagging questions at the LHC, like recognizing top quarks or boosted Ws, quarks versus gluons. So all these different object classification or object identification tasks at the LHC are now being done with much more success with deep learning. You can also explore a more tantalizing thing is to train on unlabeled data where you don't know what's in the data necessarily. And so this is a very active area too, with lots of ideas being explored, for instance, for anomaly detection, how to search for new physics, how to generate new data from old data, different things called GANs, different implementations of the thing called GANs. So these are the 2 branches of deep learning that are being brought to bear at the LHC. Okay, so in my last sort of 10 minutes or so, let me go over a couple of things that I've been working on. So just to highlight, the general trends, so there have been huge performance gains at the LHC, especially for object classification, and I'll show you an example of that. And then people are very interested in exploring, whether we can learn physics directly from the data. That's like generation or anomaly detection, and developing new and unconventional ways of searching for new physics. Okay, so the first thing I'm going to talk about is boosted top tagging, and the second thing I'm going to talk about is anomaly detection for new physics searches. Okay, but I'm running a bit out of time, so let me see what I can skip. So this is the boosted top tagging question. So just very briefly, in case you haven't seen this before, so the top quark is the heaviest quark at the LHC, and it decays basically immediately to a B quark and a W, and the W can itself decay to 2 quarks. So a single top can give you 3 jets. A jet is a spray of hadrons that originates from one of these quarks. So basically it looks like 3 sprays of particles coming out roughly in a cone. So that's what happens when the top is at rest or not moving very fast, but some of the time it can be moving relativistically fast even. And in that case, what happens is these 3 cones, these 3 jets get collimated together inside what's called a fat jet. And so that's what a boosted top quark looks like. It looks like 3 clusters of energy that are all smushed together. Might be sort of on top of each other. Meanwhile, so the tops are very interesting particles, and then meanwhile, there's like at a billion times stronger cross-section, there's QCD, giving you occasionally a jet that has 3 prongs and those also fat. So the question is that is very important at the LHC is how to differentiate between these 2 types of fat jets. And this is a classic supervised classification problem in machine learning. Okay, and the second sort of benchmark problem I want to discuss is how do you think about a new physics search at the LHC in terms of anomaly detection? And so this is how you think about it. So consider a collection of these jets at the LHC, let's say. So most of the jets will be from standard model processes like quark and gluon showering and hadronization. But a small fraction of them could be from some unknown new physics particle, some resonance that decays and gives you, like a top quark, gives you some blobs of energy inside this fat jet. So is it possible to look for anomalous jets that somehow aren't described by standard model processes without knowing ahead of time what they are? That's the question. So usually we look for these things by saying, okay, I know what I'm looking for. It's a top quark. It decays to 3 jets. It has, so I look for something with 3 lumps and a particular mass. But can I relax all these assumptions and still find an anomaly in the data? So this is a classic unsupervised anomaly detection problem in machine learning. Okay, so just very briefly about boosted top tagging, you can try to tag these tops using the traditional method is to do physics basically, and to understand what makes a top, like its mass is 175 GeV, and it has 3 lumps, whereas QCD jets tend to only have 1 lump. And so you can design a variable called n sub jettiness that measures that. And so these are 2 classic variables for top tagging. You can cut on these variables and design the best possible top tagger using these kinematic quantities. And you get something that looks like this. This is what's called a ROC curve, which shows you the signal efficiency for top tagging versus the background rejection rate. Okay, and okay, so this was the state of the art as of a few years ago, but then people started to ask whether deep learning somehow could do better. How would it do better? It would do better by taking not these engineered features, but by taking the raw information inside the top jet and the QCD jets and somehow figuring out what was important there. Okay, and a key idea here was provided in this paper from 2015, which showed that you could think of, well, it was known for a long time, of course, that you could think of a jet in the calorimeter as an image. Basically, the calorimeter is already pixelated, and the amount of energy that's deposited into these pixels is is like the intensity of that pixel. Okay, so there's a very simple sense in which you can think of a jet as an image. And so then these people realized in 2015, so 3 years after the excitement happened in the machine learning world, they realized that, wait, so we can take these jet images and feed them to convolutional neural networks and get a better better jet classifier out of that. And so this idea proved to be very powerful. They applied it, I think, to boosted W and Z tagging, but then people quickly applied it to everything they could think of. And so the work that I did with my student Sebastian in 2018 was to take an earlier image-based CNN top tagger called DeepTop, done by the Heidelberg group a year earlier, and to improve on it in a significant way to show that for the first time, a CNN-based top tagger could outperform conventional methods. So these are examples of what the images look like. So this is a top quark that you can see distinctly the 3 clusters of energy here. And this is QCD, which has one bright pixel in the middle and is otherwise more spread out. So we generated about 1 million of these QCD images and top jet images, and we fed them to a CNN. And this is what the average image looks like. You can see more clearly the 3 lumps here. So we fed these to a CNN, which looks like this. This was inspired by the DeepTop people, which was further inspired by this paper, but we did a little bit of optimization of this thing and found a better, an improved version of this that worked better. We figured out how to train this thing properly. So a number of improvements later, we got a top tagger that worked very well. This is the output of the top tagger. So this shows you basically the QCD jets look like this, are peaked at 0 top probability. This is a log scale, so this is actually very sharply peaked. And the tops, meanwhile, peak over there. So that's the output of the CNN, as it should be. And then this is the ROC curve comparison, showing you basically if you compare the conventional methods and also the previous CNN top tagger shown here, if you compare that against our final result, you see basically a factor of 3 improvement in the background rejection rate at fixed tagging efficiency over conventional approaches. So that a factor of 3 is a lot. So that's a sort of gain from deep learning that gets people excited about the promise. People are excited previously when you come up with a slightly better variable and you get 10% improvement. So if you get a factor of 3, that's when we made this plot. Well, we had better versions of this and worse versions of this. When things finally converged, settled on the factor of 3, we were very excited. Okay, so let me skip over this. The community has, since a number of us, basically contributed to a community top tagging comparison of many different approaches done on the same data set, so we can really normalize things. So let me just skip over the details of that. Suffice to say that, so we were pretty proud of our CNN result, but last November at a workshop in Fermilab, sort of on the first day, everyone was patting themselves on the back, saying, oh, like we compare all these numbers and I think we all basically have the same numbers, same performance, so maybe top tagging is a completely solved problem. And then I think on the second day, these people from UCSB came out with a top tagger. This one is basically adapted from Facebook. This one is using something called point clouds that are a very hot thing in the machine learning community right now. And they showed that they could improve the performance by a factor of 50% over everybody else's. So, and then on the third day, Gregor took everybody's taggers and combined them into a meta tagger and got another 20% or something. So I don't know if we're done or whether there's even more to learn from this, but just a sign to show you that we're dealing with a powerful tool that we don't understand here. So we should not celebrate too soon. We should keep working. Okay. So just to mention that I think I already said, but there's many more things to do besides top tagging that have been done. So trying to distinguish quarks and gluons was one of the first things that was done. Boosted W's and Z's, trying to tag B's and C quarks at the LHC is, of course, one of the fundamental things, and that's actually, I think, the first thing that's been officially deep learned by the experimental collaborations. Otherwise, these are all HEP-PH papers done by theorists. And so something we're doing at Rutgers is trying to develop a strange tagger, something that can see strange quarks at the LHC. And something that I've been doing in collaboration with people here at NTU, Janice and Cheng-Wei and Giovanna, is to try to classify charged, basically distinguish between a W plus and a W minus boson using jet charge. And that's building off previous work by Matt Schwartz and his student doing the same thing for up and down quarks. And so we can show where we basically, I think, means Janice, can show that using the idea of jet charges with CNNs buys you about a significant improvement over other approaches like VDTs at the 40% level. So it's pretty significant and should hopefully be useful for the experimentalists. Okay, I'm basically out of time, so I have like a whole nother section to talk. So I don't know, I'll figure out a way to go over that very quickly. So I'll just see what I can say here. Hopefully it's not totally incoherent. So the second thing that that we've been doing that I think is pretty interesting is something called anomaly detection for new physics searches. So that I explained basically the idea of that. And so what we played around with was our sort of toy version of this was, suppose your background are these regular QCD jets at very high PT, very high energy. And our signal that we're trying to tease out of the background without knowing what it is ahead of time are resonances that decay to 3 jets. So we took tops. We asked, can we rediscover the top using this unsupervised method? And something called an RPV gluino, that's basically a heavier version of a top. Okay, so we simulated jets of these 2 types. And what did we do with them? So our idea was, and also concurrently the Heidelberg group had the same idea, so we published on the same day. So our ideas were to use something called an autoencoder to look for anomalies. And the autoencoder, so our idea was basically, what do people in the machine learning world do to look for anomalies? They use autoencoders. Okay, let's try an autoencoder. All right, so that's literally what happened. And so what does an autoencoder do? How does it look for anomalies? So an autoencoder is basically a function that attempts to map an input back to itself. So you say, well, that's trivial. I know how to write down that function. That's f of x equals x. But no. So what makes it non-trivial is it is a lossy. It compresses. It tries to compress the information to a smaller space and then tries to decompress it. So it has an encoder and a decoder. Think of like MP3s, right? So an autoencoder is basically a machine learning algorithm to learn a compression algorithm like MP3. Like, how do you learn MP3 from using machine learning instead of figuring it out? You could train an autoencoder. And so this, because of this compression, this is not a perfect one-to-one map. And if you train basically on the difference between the two, to minimize the difference between the two, you can hope to find the optimal compression. And you can hope to find the optimal latent representation of the data. Okay, so, and then you can turn this into an anomaly detector in the following way. You quantify the autoencoder performance using this reconstruction error. That's the thing you try to minimize, the mean squared error between the input and the output. And then you train it just on the backgrounds, let's say. Or as you'll see, well, okay, I won't have time to explain it, but you train it on the data, assuming the data is mostly background. And so it learns to reconstruct the background, to compress and decompress the background very well. That would be here, let's say. And then what happens when it comes to an anomaly that it hasn't seen before? It just freaks out and it doesn't know what to do and produces some random garbage. And so the random garbage sits here. And so that's how you can use it as an anomaly detector. You can cut on the reconstruction error, and everything with a high enough reconstruction error could potentially be an anomaly. Okay, so we explored a number of different autoencoder architectures, but the one that worked the best for us was, not surprisingly, a CNN-based autoencoder, where instead of the classifier, which would have stopped here, you basically flip the CNN around, and you do something called upsampling to produce usually a blurry version of the input. Okay, so this is a plot showing you how the CNN autoencoder performs on the backgrounds that it's been trained on, input and output, and the two different signals that it doesn't know anything about. It's never seen before. And this is the difference of the two, showing you that indeed, when it sees the backgrounds, the error is larger. And so this is a more quantitative version of that. So there's a histogram of the reconstruction error, showing you, this is a log scale, showing you how well the QCD is reconstructed. And then for the signals that it's never seen before, there's this big honking peak there. Okay, so it's really, so that was the main result, is that this autoencoder idea really does work on realistic signals, and potentially you could rediscover the top this way, which would be a cool proof of principle. Okay, so the even cooler thing that we showed is that you could train the autoencoder on data that had been, on fake data, basically, which was the backgrounds contaminated with a small amount of signal, up to 10% even, and that it would still work as an anomaly detector. Basically, as long as it doesn't see enough signal, it'll learn to reconstruct well still the dominant data, which is the background. Okay, and so this is showing you then, again, in terms of the Gluino, what happens to the jet mass distribution before and after a cut on the autoencoder loss, the reconstruction error, and you can see that the peak, we studied Gluino at 400 GeV just as a benchmark, and so you can see that the peak is greatly enhanced after you cut on the autoencoder loss. And so yeah, you could really potentially discover new physics this way. You could combine an autoencoder, say, with a bump hunt in mass. You cut on the autoencoder loss to clean away the boring backgrounds, and then improve the signal to noise by a lot. Okay, this is just a proof of concept. We didn't, there's lots of experimental issues here that we didn't consider, and we just think hopefully it'll be inspirational to serious people that actually have to do this in the experiment. Okay, so sorry to go a few minutes over time. Let me just summarize. I think, so deep learning has revolutionized the field of artificial intelligence and is changing our world. And it's given birth to a number of stunning real-world successes and applications. And hopefully I've convinced you or shown you that the revolution is coming to high-energy physics, and probably coming to your field as well. In this talk, we gave an overview of deep learning applications to the LHC, and then we focused on two interesting applications that my collaborators and I have been working on. That's top tagging with jet images, which is an example of supervised machine learning, and deep autoencoders for open-ended anomaly detection, which is a prime example of unsupervised learning. So thanks.
Okay, thank you, David. So we're open for questions, comments.
With the fixed number of parameters, why is it better to have more layers in the architecture?
I mean, yeah, that's a great question. So take something like this, for instance. So again, the short answer is nobody knows, I think. A lot of these things are just empirical, and the intuition or theory behind this, which maybe has some evidence for it, but I don't think it's by any means rigorous, is that as you go deeper, the algorithm is capable of learning more and more abstract notions. So the evidence for this is you can sort of look at the activations at the deeper layers. You can sort of see in some examples more abstract features emerging. So for instance, let me make this concrete. So the earlier layers may learn simple features like edges between light and dark, or dots, like spots and things, circles and simple shapes. And then as you go higher and higher, it may learn more abstract quantities like noses and eyes. So you could actually look, it's a little bit creepy, but you could look and see like eyes start to emerge in the deeper layers. So it's learning things like wheels and chairs and things. Yeah, so shape, like real world shapes. So that's the idea, maybe, is that it's learning more abstract things as you go deeper and deeper. Yeah.
So this actually leads basically to my question, which is, so like normally, like in all these particle physics experiments, they're really interested in making sure they totally understand all their systematics and that their analysis is unbiased, and they do all this blinding of the data and stuff. But then, given that, I mean, that's using statistical methods that are normally pretty well understood mathematically. But then here you're using something that, like really, no one understands the, like the sort of mathematical rigor behind it, if there is any. So like, how do you know, how do you avoid that sort of problem?
Yeah, well, so first of all, I'm not an experimentalist, so my understanding of systematic errors and things is very uninformed. I've never had to struggle with those things before. And it's true that, like dealing with signal Monte Carlo or whatever is the easiest part of their job. They'll tell you easily, they spend, the largest fraction of their time easily dealing with these systematic errors. Yeah, so I think it's a fair question. As far as the first thing I talked about, top tagging, is concerned, I think they believe they have that under control. So if the algorithm is basically a black box, and they train it on, say, simulations, but then in the data they have a good control and signal sample where they're already sure they know the answer, then they can apply the black box to the control and signal regions, and basically compare how well they do in the data to how well they do in simulation. And so they don't have to necessarily know, I think, all the parameters in the black box to measure systematic errors associated to top tagging. I believe that's the way it works for that. As far as the autoencoder thing, that's pretty far out there. So yeah, so I think that, I think the experimentals are very interested in this, at least that's what they say, but they also say we have no idea, yet how to use this for anything. But I think people are maybe trying.
Any other questions from students in particular? Or all the students are in deep thinking? Well, if there's no...
So I'm curious about that. When you prepare a sample, a template for learning, or machine learning or deep learning, so how, suppose it's kind of biased. So can a deep learning learn this is a bias?
So by which you mean, I guess, that the simulation, you mean prepare a simulation sample, for instance, or even a subset of the data? Yeah, so you could ask, how accurate are my simulations, or how accurate was my slice of the data? How representative was it to the real thing? Yeah, so can the machine learning algorithm learn that the slice you gave it was biased? I'm not sure. I don't know. I mean, I suppose, well, what you do in this game is you train it on a fixed training sample, and then everything else is for evaluation. So I guess you'd be asking whether the only way it could learn that it was biased, know that it was biased, is by looking at the test sample, the real thing you're interested in. But then you're not allowed to take that test sample information and feed it back, because then that becomes part of your training sample. But maybe you could do something where, if your data set is growing, you could sort of feed it bigger and bigger chunks, and you hope that converges to something. But otherwise, I think what they do in practice is they accept that it's going to be biased, and then they try to measure the bias. And if they can measure the bias and it's stable, then actually it's not a source of systematic error anymore, because they can correct for that. What's problematic is when the bias is, so if it's a constant bias, they're happy. So if the bias depends sensitively on lots of things, that becomes a big source of systematic error for them. Yeah. So actually, bias data is not really the problem. It's bias that you don't understand. That's the problem.
Sorry, I'm a little bit curious about how can you use the autoencoded architecture to find new physics? Because it seems like you encode the images or the data into latent space, and suddenly, if there's an anomaly happens, you get some weird numbers in the latent space. But how can you be inferred, like what's going on in the real world by these numbers in latent space?
Yeah, so, well, first of all, the way we would propose doing it is, I mean, there's lots of different approaches you could take. You could try to do anomaly detection directly in latent space. That's another promising idea. What we were proposing is to do the anomaly detection on the, basically on the output of the autoencode, this reconstruction error. So then I think your question becomes, you know, how do I know what's the, if I'm looking for an excess in the reconstruction error, how do I know what the prediction of the standard model is if I don't rely on any simulations? So how do I know what to expect and what an excess actually means? We have to be able to predict the background, basically. And so that's why, so I ran out of time, that's why we proposed to combine the autoencoder with some other variable like jet mass and do a bump hunt, do a search for an excess in this other variable like jet mass, and that way you can use a sideband method to estimate your background. So basically, if you have some other way to estimate your background that's orthogonal enough to the autoencoder, you can combine the two approaches. So that was our idea, but I'm sure there's lots of other things you could try. Nobody has any crazier questions?
Any? Okay, if not, let's thank Professor Shi again.